Amy, if you want to start sharing your screen, then we'll be ready to start in about 20 seconds or something.
Okay.
Dean, unless you have something you want to say first.
I just want to say thank you very much to Mark DeRosa for stepping up and being the chair in the last section. We'll now continue with magnetic flux in the Sdo era from emergence to eruption, and this will be chaired by Todd Huxema. It's all
Welcome
yours,
back.
Todd.
Thank you, Dean. Welcome back, everybody. Thanks again for attending. I'm looking forward to the rest of this meeting this morning. There were several talks earlier in the morning that tied into the topic of this session. So I hope you all find it as interesting as I do. I wish we could see each other all in person and that we could have a lot more talks contributed, but we've tried to select some things that we thought would be of general interest and really represent the range of HMI and magnetic field science in the Sdo era. So our first speaker is Aimee Norton, magnetic flux in the Sdo era from emergence to eruption. It's a 30-minute slot. She has about 25 minutes for presentation and 5 minutes for discussion at the end. And then we'll have 3 other talks after that, each of which is going to be 20 minutes with 15 minutes of speaking and 5 minutes of discussion section. So Amy, I will give you a warning at about 20 minutes and you need to wrap up in 5 and take it away. Thank you.
Okay, thank you. Can you hear me okay?
Yes.
Okay. I'm delighted to be a part of this virtual workshop. I look forward to a time when we obviously can collaborate again in person. I'm going to be talking about magnetic flux in the Sdo era. And thank you to Robert Cameron for nicely introducing flux emergence. Of course, magnetic flux is an important topic because it is the flux in the photosphere that's a direct consequence and measure of the solar dynamo. I'll be touching on these topics today. There's a lot that, oh, I'm having a difficulty advancing slides. Hold on.
You might try your arrow key.
I am trying my arrow key.
You're on the movie. You have to click out of the movie.
Okay, just a second here. I'm going to stop sharing and start again. Did that stop sharing or not?
Yes.
Yes.
Okay, so now it's not being shared. Is that true?
True.
Okay, it's just a second. Share screen. Okay, let's see if this works better. Okay, okay. Looks like it's advancing slides. So I'm going to be talking about, you can see the screen, everything okay now?
Perfect.
Okay, so I'm going to be talking about sunspot flux emergence rates and rise speed into the photosphere, also about bipolar tilt angles and tilt quenching, and complex regions such as anti-hail regions, rogue sunspots, and delta spots, and active longitudes. Most of the work that I'll be talking about today, and also the papers that I point to that are other people's efforts, will be using HMI and Sdo data. In addition to the regular full disk data, that is the 45-second continuum intensity magnetograms and Dopplergrams that you're familiar with, and the 12-minute Milne-Eddington inverted vector data. There are also the SHARPS data that many of you are using, but I wanted to point out their availability again. They are the space weather HMI active region patches, and you see data that are representative of them here from October 2014. They are tracked magnetic patches. Not all of them are sunspots. So since Sdo has started taking science data, the instruments or HMI, the full disk instrument, has observed over 1,700 sunspot groups. And there have been at least 4,300 distinct HARPs, which means that not all of them contain sunspots, and about 2,500 of them are ephemeral regions, or regions that do not have an intensity counterpart. So I'll be using this data to show some flux emergence rates results. So transitioning now to the science. This is data that is from the SHARPS data. It is the sunspot 11428 from March 2012. In the upper panels, you can see the continuum intensity on the left and the radial field values on the right. And you can see on the bottom panel, the time that we are following it for over 200 hours. And what we are looking for, my collaborators and I, were to examine how flux emerges and see if we could find a value that could be compared to simulations. And so in the bottom panel, you can see the flux emergence rate. In the red lines, you can see the flux that's in the umbra. And in the green lines, the flux that's contained in the umbra and penumbra. And in the blue lines, that flux that's contained in the entire region. And the solid line is representative of the leader or preceder spot, and the dashed lines are representative of what's in the follower spot. So the results from this paper are in a paper in 2017 by Norton, Jones, Linton, and Leake. And the simulations have informed us that not all the flux in the system will emerge into the photosphere. Some of it doesn't make it. The flux can thread in and out in observations in a way that the observers see more flux than is actually contained in the flux tube at the bottom boundary. And also that much of the flux is canceling during emergence. So it's a dynamic quantity that we're measuring here. To talk a little bit about flux emergence in general, the flux is rising through the convection zone due to magnetic buoyancy, and there's a strong stratification. So any sort of flux that emerges from the bottom of the convection zone is experiencing spreading horizontally or pancaking. And as it makes its way through the convection zone, it interacts with the turbulent convective flows. It could be shredded or have different properties imparted to it from the convective flow. It's considered to be a two-stage rise process, at least. The first stage is the rise through the convection zone due to buoyancy. And then when it comes close to the top where it's going to emerge into the photosphere, the flux halts or slows drastically. In the second stage, the rise into the photosphere, it needs to experience another instability, probably the nonlinear development of the undulate mode, and Kalman Knizhnik is going to be talking about that based on a paper that they've just published later in the session. So it's still a point of contention whether the flux must experience another magnetic instability or whether convective motions can assist in pushing it through into the photosphere. In the simulations, the emergence rates are often affected by the geometry of the flux that's being advected across the bottom boundary, as well as the rate at which it's being advected across the bottom boundary. So some more results from that study are shown in the top two panels here. Active region 11428 is on the left and 11460 is on the right. Again, we're looking at the flux in the leader and the follower spot as a function of time. Notice that the top two panels are 200 hours, and the observations are compared with a simulation of Rimpel and Chung from 2014 on the lower left side here. And they also have the same meanings for their colored lines, with the red being what's contained in the umbra, the green, the penumbra and umbra, and the blue in the entire region. Rimpel and Chung advected a semi-torus tube across the lower boundary at 500 meters per second. And as you can see in comparing the slopes of the lines, the rate of flux emergence in the simulation is faster, and the time scale is shorter than what is seen in the observations. Another thing that you might notice here is that the green lines in the simulation contain less flux. The penumbra does not seem to form as soon and contain as much flux as what we observe in the observations. So to put this value in some sort of context with other values that are reported in the literature is this rather complicated plot, but I think it's worth spending a few moments on. And it shows the flux rate on the y-axis, the flux emergence rate, and compared to the flux in the system on the x-axis. The results from the 2017 observational paper that I was just showing you are represented here in, it doesn't look like my mouse is showing up. I'll just tell you. In the blue diamond, that is a rate of about 7 times 10 to the 19th Maxwells per hour. And then other reports in the literature are shown here. A Toriumi study using HMI data as well from 2014 is very nearby, just to the left of the Norton result. All the blue symbols are observational and all the red symbols are simulations. There's ephemeral region down in the lower left corner of the plot, and that's how fast ephemeral regions were seen to emerge from Hagenaar and Yang and Zhang. There's penumbral formation with the blue star, and more observations from HMI from Centennial Elliott with this blue cross. And so if you compare those with the simulations, which are all the points in red, you can see just in general that the simulations are showing a higher flux emergence rate than the observations. Of course, simulations have the benefit of being able to isolate one aspect and change it and see what happens. They see that having a higher twist emerges flux faster, having higher flux emerges flux faster. And then Zhudong Sun and overplotted these stars on the upper right side, which are some very exceptionally large regions on the sun, 12673 and 12192. And you can see that they have a very high flux emergence rate. So in general, stronger flux regions emerge faster. A kind of marvelous extension of this work was done by Namakate, who looked at Kepler data and overplotted star spot flux emergence rates with fast rotators being blue and slower rotators of greater than 7-day periods being red. And the idea is simply to show that star spots may emerge, with similar conditions that sunspots do. Of course, with stronger flux, if you're observing the darkening of the stars spots. But I thought that was kind of a marvelous extension of that work. So the takeaway points from this flux emergence study are that stronger flux regions emerge faster. Simulations show faster rates and shorter timescales. The higher twist, higher fluxes and flows cause faster emergence. A surprising study correlated star spots and sunspot emergence rates. And a question I think that's still outstanding is, how can we determine if the flux emergence rates are dominated by convective flows or the development of the instability? So I wanted to say one more thing about flux emergence, which is to highlight a result from Bert Schunker et al. In 2016 that you've probably seen, but I thought it was worth amplifying the message again. They studied 105 emerging active regions with HMI, looking at the surface flows and looking at the diverging flows at the surface prior to the emergence of an active region. And they reported an upper limit of 150 meters per second for the rise speed of the active region in that 20 megameters just below the photosphere. They also said that the flux prefers to emerge on the prograde side of an east-west aligned converging flow lane, like a supergranular cell. And I just thought this result was really interesting. The panel is showing an observation on the left panel, the active region 11158, and compare similar scenarios in their simulations where they're advecting a flux tube from a bottom boundary 20 megameters below at either 500 meters per second in the middle panel versus 70 meters per second in the right panel. And these panels are showing the flows diverging in red and converging in blue. And the arrows, like the largest arrow in the center, is about 400 meters per second. So it's basically showing that the observations are consistent with a rising flux rope or flux tube of about a convective velocity of 70 meters per second. I wanted to point out that there may be some room to compare to the Toriumi results in 2012 and 2014 that report very strong horizontal flow fields for active regions, with about a third of them of emerging active regions showing 1.5 to 3 kilometers per second. But this, they might be comparing different things. The Birch study is looking at 7-hour averages, and the Toriumi study is looking at instantaneous flow. So there could be some room for comparison there to understand better how the flux emerges. So do observations of slower rise speeds and slower emergence rates sort of dam the thin flux tube models that predict rise speeds of 500 meters per second near the photosphere? I would answer no. It only indicates that the buoyancy of the flux tube isn't as high as the values used in simulations. My understanding of that comes from discussions with Mark Linton. And I wanted to ask a question, who's continuing the thin flux tube work? People could add that to the chat. I'm just not aware of who's working on this topic right now. I was aware of the Weber, Fan, and Misch results from 2012, but I know Maria Weber took a job teaching and is not doing active research at this time, I don't think. Okay, so moving on to the next topic, which is Joy's law and tilt angles. The tilt of the bipolar magnetic regions on the sun's surface is evidence of the alpha effect, the generation of the poloidal to the toroidal. Oh, sorry, generation of poloidal from the toroidal. And Joy's law is the dependence of the tilt on latitude, which is often explained by the Coriolis force acting on flows within the rising flux tubes. It's not perfectly understood. The high scatter is thought to be caused by interactions with the turbulent convection. But it's a really important aspect to our understanding of the dynamo model. The modelers use Joy's law to govern the emergence of their magnetic flux, and the outcomes of the tilt angles of their regions rely on Joy's law. Again, I wanted to highlight some work from many of the researchers at MPS. The Shunker et al. 2019 studies show the tilt angle developing over 2 days after emergence for 154 active regions. So the plot on the left here is showing the leader and the follower, the leaders in blue and the followers in red. Time is progressing along the arrows. So you're seeing the two regions, the follower and the leader, moving apart. And it's a very interesting way to look at this. I've never seen the foot point separation broken down into the X and the Y directions. And the way they interpret this is that at the very beginning, it's the emerging east-west, just because you're seeing the apex of the flux tube, it's separating quickly as the apex of the flux tube. This is shown on the right-hand side with time progressing upwards. The apex of the flux tube breaks through the surface and you see it separate quickly, and then there's tension on the field lines trying to straighten them until the foot points stop moving away from each other as they reside right above where they're anchored. Makes one wonder how deep these are anchored. I don't have an answer for that, but I wanted to say that many of the results of their study can be seen in a study I did with a PhD student, Bruce McClintock, and this is a little bit too much information on this slide, but I just wanted to point out the similarities. If you look at the upper right plot, the large bipoles also show that they emerge roughly east-west with the tilt angle on the y-axis and time running along the x-axis. We chose to look at this data with a 0 point in time being the max area of the region, and then sum everything up backwards for 3 or 4 days and forwards for 3 or 4 days from the max area of the region. So you can see that they do emerge roughly east-west and the tilt angle develops, but not so much for the small bipoles and medium bipoles. They act a little bit different. But we also see that the foot point separation settles in about 3 or 4 days, and they don't move further apart than about 70 megameters. And so now I'm going to just briefly mention tilt quenching, which is a way to limit the cycle amplitude. If you have a very strong solar cycle, it appears, as shown in this plot below, the strength of the cycles on the x-axis in area of sunspots versus the mean tilt of that cycle. And this is reported in at least 2 papers, McClintock and mine, and Dazius Buig. And it's a way, if the stronger cycles produce lower mean tilts, it's a way to quench the amplitude so that the next cycle is not stronger. This work is still going on. This is a study by Jha, Karak, Mondel, and Banerjee, looking at tilt quenching from space-based data using MDI and HMI data. You can see their histograms of the bipolar regions that they observed, with 2 distributions, one being sunspots and one being bipolar regions without continuum intensity features in the blue. And basically, they show that the slope of Joy's law is reduced for the stronger fields, which are the lower plots. They plot the slope of Joy's law as a function of limiting the sample to those fields with Bmax on the x-axis or flux on the x-axis on the right-hand side. So it's an indication that tilt quenching is happening even in these two relatively weak cycles. So now I'm going to, how much time do I have left, by the way?
You have about 5 minutes left, 6 minutes.
Is that including questions?
No, that's before.
Okay, perfect. Okay, so talking about tilt angles, there's a population of bipolar regions that emerge with the completely opposite tilt than expected. So the bipoles emerge in the hemisphere in the wrong direction, with the leader being the opposite polarity than what you would expect. And some work recently by McClintock, myself, and Lee has shown that, maybe not recently, in the last cycle, has shown that we find that there's more anti-hail spots than previously reported. We find about 8% of regions are showing anti-hail properties, which is lower than what's been reported by others, being about 4%. And this plot shows, it's sort of the butterfly diagram, but with the tilt being represented, and you can see the anti-hail spots when they're the opposite color, and like the blues in the sea of orange and the reds in the sea of blue. And I recently looked at the rest of solar cycle 24 and again find roughly 8% in the north and south hemisphere for anti-hail. And why is it important that we have these strange spots? And Robert Cameron talked about this earlier, that a very large anti-hail spot that emerges close to the equator can be really influential in the development of the global dipole field and cause future cycle amplitude variations. So there's some people that are studying this in detail, Melinda Nagy, Christophe Petrové, and others. And the terms rogue active regions, and this plot shows a simulation with the pseudo sunspot number. So you can see the cycles, and in the middle cycle, they introduce bipoles with certain properties at different times in the cycle. And then you can see how the next two cycles evolve based on the influence of that one bipole being placed in the study at that point. And so it's really interesting to think that, you know, a single rogue active region could really influence the next solar cycle and the next. There's an ISI team that is working on this, dedicated to studying the dynamo effectivity of solar active regions. And unfortunately, we haven't been able to meet due to COVID, but we're still managing to get some work done. So I only have 2 more points before I conclude. Delta spots are another strange manifestation of active regions. They represent a very low percentage on the disk during a solar cycle, but they're very influential because they're so complex. They are often the source of flares and CMEs. And Mark Linton and Colin Kniznik, myself and Lucas Tarr have been looking at this, and we're having some difficulty sort of merging the simulations that show kind of a tidy flux rope with a high twist that experiences the kink instability with what we're seeing in the data. And it's very hard to find an example that looks like a really nice kink instability. And instead, what we find is a really messy situation with, you know, what looks like 2 different flux systems colliding. And a perfect example of that is 12673, where you see this nice, well-behaved sunspot sitting there, and this region emerges from below that's very complicated and just sort of creates many delta systems within that. And there's been some active discussion and papers on the collision of flux systems. Yeagley and Norton 2016, Toriomi 2017, and Nick Bosch 2019 all discuss the various configurations of flux ropes that can lead to delta spots. One more paper I wanted to point out was this recently accepted paper by Dick Potty, which should be available for public in the journal very soon. And she's been doing work with colleagues on looking at how the instabilities of the toroidal field in the near the tachocline, experiencing using the shallow water model to look at the instabilities that are experienced there that cause warping and tipping of the toroidal field, then manifest at the solar surface by active regions, showing active regions emerging at the point where there's a bulge in the tachocline field. And so it's basically fitting the sunspot patterns to the modeled instabilities deep in the interior. And so a simple understanding of it is if you have an m=1 instability, you just have a tipping of the toroidal field. And at the apex of the tip, you may, at either side, you may be seeing sunspot regions emerge. And these instabilities persist, so they could be the source of active longitudes or nests. And the simulations and the modeling are showing that there's a periodic behavior. And so it's linked to the bursty activity, like the Riger type activity of 6 to 18 months frequency, where you get activity is seen in the sunspot numbers and the space weather records.
We have about a minute left, Aimee.
Okay, well, I have a conclusion slide here, and I kind of tried to cover a lot of information. So my conclusion slide is just a nice one that says my cycle 25 prediction is that from the impressive work from all the people I've mentioned here and the ones that I didn't get to mention that are doing impressive work worldwide and the collaboration between so many groups, I predict we'll see numerous scientific breakthroughs during cycle 25. And the last thing I'll mention is that I'm part, and Stanford is part of the COFFEe's Consequences of Fields and Flows in the Interior and Exterior of the Sun NASA Heliophysics Drive Center. And it's a really fun effort where we're trying to combine a lot of expertise and our understanding of subsurface flow fields, modeling the surface magnetic field connection. And here's the website, and contact us if you're interested. I'll stop for questions.
Okay, thank you, Aimee. That was a really nice review, and thank you for that shameless plug for coffees at the end. Do we have any questions? So looks like we have one from Lisa. I'm surprised that the smaller active regions have a more constant tilt than the large active regions. I would have expected the opposite, since the smaller active regions should feel more turbulence from the convection than the larger active regions. Do you have any comment on why the larger active regions might change tilt more?
The scatter is much higher in the smaller active regions, but I'm not quite sure which plot she's referring to. If it's the one as a function of time that I showed with McClintock and mine, it's we found that the larger active regions continued to change tilt for longer than the smaller bipoles, but there is a lot more scatter in the tilt angles of the smaller bipoles.
Yeah, and it looked like the trend of the larger ones wound up with a larger tilt than the other ones too. It was interesting.
Yeah, it might be a little bit in contradiction to the work that's being done by the John Vidya Karat.
Mm-hmm.
I have to look at that. Sometimes just the way you average your data can show different results. I mean, we looked at, we were averaging from the time zero being the maximum area, which other people aren't doing. They're starting time zero is when the bipole first emerges.
Mm-hmm. Yeah, that does make a difference. We have another question from Manolis Jojolis, which is, Aimee, could you comment on why some active regions show a plateau at full development, whereas others go directly into the decaying phase?
I don't know why they show a plateau. I know that when a sunspot group starts to lose its penumbra, its decay begins then. But in terms of why some sunspot groups are stable and others are not, I don't know the reason. I can guess that maybe it has to do with how deeply they're anchored and the flows around them keeping them stable or not.
Okay, great. We'll take one last question from Masha. has anyone looked at flare and CME activity of hail versus anti-hail regions?
I'm sure they have. I'm sorry, I didn't.
A little bit
cover
off
it.
the
I
top.
know that there is a common condition pointed out a relatively new paper, maybe in the last 6 months, that is a catalog of anti-hail regions, and I can send you that reference, and it may have in the catalog if what kind of activity is associated with each of those regions.
Okay, well, thank you very much, Aimee. That was a really fine talk. There's several comments in the chat that you might want to look at
Okay, thanks.
as you go on. All right, if you'll stop sharing, then we